Good morning to all. I am happy to meet you again with a new topic, radioactivity. Radioactivity is discovered by Henry Becquerel in 1896. He was using uranium salts wrapped in a block paper and kept on a photographic plate. After developing the plate, he found the plate got exposed. He concluded that this was due to invisible radiations came from the uranium salts, named is radioactivity. You can see the right side, the exposure of the photographic plate from the uranium salts. So what is radioactivity? Radioactivity is a spontaneous disintegration. Unstable nuclei perform radioactivity with the emission of either alpha or beta and gamma rays. Certain extent, electron capture and internal conversion also contribute to radioactivity. During radioactivity, the atom changes its atomic number and its chemical identity. A radioisotope is an unstable atom that performs radioactivity. There are two types of radioactivity called natural radioactivity and artificial radioactivity. Natural radioactivity, the example is radium-226. 226 is the mass number. Artificial radioactivity was invented by Curie and Juliet in 1934. The best example is cobalt-60 used in teletherapy machines in radiation treatment. Radioactivity is measured in becquerel, that is the SI unit, or the special unit Curie. 1 Curie is nothing but 3.7 into 10 power 10 disintegration per second. It is equal to the activity of 1 gram of radium. The 1 becquerel equal to 1 disintegrations per second. Radioactive disintegration follow the relation dN by dt equal to minus lambda n. dN by dt is the rate of disintegration, lambda is the decay constant, n is the total number of nuclei. Different nuclei will have different decay constant, and the equation in general can be written as n is equal to n0 e to the power of minus lambda t. That means n0 is the original number of nuclei, n is the number of nuclei at a time t, lambda is a decay constant, e is an exponential function, minus sign indicate that during radioactivity the number of nuclei is decreasing in order. So if 100 is the number of nuclei, after time it decreases exponentially. So from that one can conclude half-life period of the radionuclei. That means the time taken for half of the number of atoms to disintegrate. Suppose if the number of nuclei originally 100, then what is the time taken for 50? The time is called half-life. This slide shows the relation between half-life period and the decay constant. Half-life period of an isotope is equal to 0.693 divided by decay constant. This shows you the different isotopes radioisotopes we are using in medicine. Radium-226 having 1622 years of half-life, cobalt-60 5.26 years, cesium-137 30 years, iridium-192 74 days, iodine-131 8 days, technetium-99m 6 hours, F18 110 minutes. Apart from half-life, there is also a parameter called mean life for isotopes. What is a mean life? It is a lifetime of an imaginary source which decays at constant rate equal to the initial activity. There is a relation between the mean life and half-life. Mean life of an isotope is equal to 1.44 into half-life period. Apart from that, radioisotope is also described in terms of specific activity. What is specific activity? It is activity per unit mass. It is expressed in becquerel per kilogram. If the isotope has higher specific activity, miniature source can be made easily for clinical application. Radioactive material can be divided into in terms of series. There are three series of radioactive material, that is called uranium series start with uranium 238, actinium series start with uranium 235, thorium series start with thorium 232. In medicine, we are more interested on uranium series. Radium is the sixth member of the uranium series, which is obtained from the ore pitchblende. Radium gives series of daughter product including radon 222 and ends up with lead 206. In equilibrium, there are two types of equilibriums are present. One is called secular equilibrium and transient equilibrium. What is secular equilibrium? The half-life of the parent is much longer than that of a daughter is called secular equilibrium. For example, radium 226 and radon 222 as a parent and daughter. You can compare the half-life 1622 versus 3.8 days. In the case of transient equilibrium, the half-life of the parent is not much longer than the daughter. You can take example molybdenum 99 and technetium 99M. You can compare the half-life 67 hours versus 6 hours. Coming to the alpha decay, in alpha decay, the atomic number decreases by 2 and mass number reduces by 4. You can see the example uranium 238 decays with alpha. This is the alpha particle, doubly ionized helium atom. It goes as a daughter 234. Atomic number greater than 82 mostly undergo alpha decay. Radium decays to radon with alpha decay. Radon is also a radioactive and it decays with alpha. Alpha properties, it is a doubly ionized helium atom, positively charged, gives intense radiation, it has short range, it belongs to high LET radiation. LET means linear energy transfer. A sheet of paper can stop alpha rays very easily. In beta decay, there are two types of beta decay. One is beta minus decay and beta plus decay. Let us see the beta minus decay now. There is no beta particle inside the nucleus. But how the beta comes? Let us see that a neutron in the nucleus is converted into proton and electron. As a result, atomic number increases by 1, mass number remains the same. Example, you can see here. Radium 228 goes to actinium 228. During that process, an electron and antineutrino is emitted. It have all possible energies and the mean energy is given by E max by 3. It is negatively charged, ionized matter, it has short range, but the range is higher than the alpha particle. A few millimeter of aluminum can stop beta rays. Coming to the beta plus decay, in contrast, a proton in the nucleus is converted into neutron positron. The neutron is kept in the nucleus and positron is emitted as radiation. You can see the example sodium 22 emitted as neon 22. The atomic number decreases by 1, mass number remains the same. During the decay, an electron and neutrino is emitted. It is positively charged, have short range. Its range in solids and liquids is 2 to 3 millimeter. A positron combines with an electron and comes to rest, which we call it positron annihilation. So it's a very interesting topic. What is positron annihilation? A positron combined with an electron, the mass is converted into energy and emitted as 2 gamma photons in 180 degree up to maintain the momentum. You can see the picture, the positron and the electron combine together and produces 2 gamma ray photons of energy 511 kilo electron volt. This is a very good example is for the conversion of mass into energy as stated by Einstein. You find applications in the positron emission tomography as well as the PET-CT. Basically, fluorine 18, the fluorodeoxyglucose is used as a positron emitter most commonly. Let us discuss about the gamma rays, how the gamma rays comes. After radioactivity with alpha or beta decay, nuclei comes to an excited state, that means higher energy state. The nucleus from the excited state decay to the lower energy state with the emission of gamma rays. You can see in the picture, cesium-137 decays with the beta, it goes to the excited state, and decays with the gamma rays goes to the ground state as a barium-137. There is no change in atomic number and mass number. This is known as isomeric transition. What is isomeric transition means? It is a transition without change in atomic number and mass number, only energy is released. Example, cesium-137 and cobalt-60. Let us see some of the properties of gamma rays. Similar to X-rays, it belongs to electromagnetic radiations of shorter wavelength in nanometer. It have no mass and charge. It will travel in straight line at the velocity of light. It will travel about 3 lakh kilometers per second, not deflected by electric and magnetic field since it has no charge. It is highly penetrating. Its penetration is 100 times higher than beta rays. It affects photographic films and cause fluorescence in the crystals. It does ionization, excitation, which causes biological damage in cells and molecules. That is the reason we are concerned about radiation protections while using the gamma rays. What is the difference between X and gamma rays? X-rays are basically extra nuclear process. That means outside the nucleus, the X-rays are produced. The interaction with the nuclear field somewhere around here, Bremsstrahl lung is produced. Electron transition between orbit somewhere around here, characteristic X-rays are produced. Whereas gamma rays are intranuclear process, that is concerned with the nucleus. So basically to emit gamma rays, you must have a source of radioisotopes and you should perform radioactivity. Both X-rays and gamma rays have similar properties. It is used in medical imaging as well as for medical treatment. There are two more decay called electron capture and internal conversion. Let us see one by one electron capture. Where electron capture takes place, nuclei deficient of neutron undergo electron capture. It absorbs its own K or L shell electron. The electron combines with the proton and forms one neutron and neutrino. The neutron is kept inside the nucleus and the neutron is emitted. As a result, the atomic number decreases by 1 but mass number remains the same. The vacancy in the K shell follows electron transition from higher orbit, leads to emission of characteristic X-rays and Auger electrons. Atoms which is having atomic number greater than 30 always favors characteristic X-rays, whereas atom less than 30 always favor Auger electrons. This is an example for electron capture. You can see iodine 125 go by electron capture and followed by gamma radiation, and mostly electron capture is heavier proton rich nuclei undergo electron capture. Most common in valence daughter transition energy less than 1.02 MeV. Examples are iodine 125 and thallium 201. Last but not the least is the internal conversion. What is internal conversion? It is the emission of gamma rays by the excited nucleus. Excited nucleus emits gamma rays. These gamma rays are passed on to one of the orbital electrons. That electron is ejected from the atom. There is a vacancy that follows characteristic X-rays and Auger electron as before. What are the conditions for internal conversion? The released energy must be equal to the binding energy of the electron plus kinetic energy. Daughter nuclei after radioactivity have excess energy may perform internal conversion again. In summary, radioactivity is a spontaneous disintegration of unstable nucleus. It involves alpha, beta and gamma decay. Of course, at an extent, electron capture and internal conversion also contribute to radioactivity. Becquerel and Curie are the units of radioactivity. Gamma rays are due to an intranuclear process. It is used in cancer treatment as cobalt-60 therapy. It is also used in nuclear imaging as gamma camera and PET-CT. Of course, using the radioactivity, one can come across radioactive waste. This waste requires safe disposal to minimize the radiation hazards. Thank you very much for listening. I hope you understand the topic. We will meet with another topic in the next week. Kindly subscribe and succeed. Thanking you.